Right now, at this exact moment in time, a spacecraft the size of a small car is drifting through the emptiness between the stars, completely alone, picking up sounds that have absolutely no business existing in a place where almost nothing exists at all. Subscribe now before we go any further, because what NASA has confirmed about what Voyager 1 is hearing out there is one of the strangest, most quietly remarkable stories in the entire history of space exploration. Let's start with where Voyager 1 actually is, because most people genuinely have no idea how far this machine has gone. Voyager 1 launched on September 5th, 1977 from Cape Canaveral in Florida, nearly half a century ago. Its original mission was straightforward: fly past Jupiter, fly past Saturn, collect data, and send it home. Nobody at NASA seriously expected the spacecraft to still be operating in 2026. Nobody expected it to still be transmitting anything at all. But right now, Voyager 1 is approximately 25.4 billion kilometers from Earth, roughly 16 billion miles. To put that in perspective, the distance from Earth to the Sun is about 150 million kilometers. Voyager 1 is currently more than 160 times farther from the Sun than we are. Its signal, traveling at the speed of light, takes more than 23 hours just to reach us. And NASA projects that on November 15th, 2026, that signal travel time will hit exactly 24 hours, making Voyager 1 the first human-made object in history to sit one full light day from Earth. Suzanne Dodd, the project manager at NASA's Jet Propulsion Laboratory, has explained it simply: send Voyager a good morning message Monday morning, and you'll get its reply Wednesday morning. That's not a metaphor. That is the actual operational reality of managing a spacecraft in interstellar space right now. Here's what makes all of this even stranger. Voyager 1 isn't just far away. It's in a completely different region of the universe from anything humanity had directly sampled before. In August 2012, Voyager 1 crossed the heliopause, the outermost edge of the heliosphere, the enormous bubble of solar wind and magnetic influence our sun produces, extending well beyond the orbit of Pluto. Crossing that boundary made it the first spacecraft in human history to leave the heliosphere and enter what scientists call the very local interstellar medium, the actual space between stars, not the edge of the solar system, but interstellar space itself, where the sun's influence gives way to the wider fabric of our galaxy. And out there, in that almost unimaginably empty region of space, something unexpected happened. Voyager 1 heard something. Not with ears, not through air. There is no air out there, and sound, as we understand it, can't travel through vacuum. But the spacecraft's plasma wave system, an instrument built with two antenna rods stretching about 10 meters behind the spacecraft, was designed to detect a different kind of wave entirely. Plasma waves, ripples, and vibrations moving through the thin, ionized gas that permeates even the emptiness of interstellar space. When converted into audio by scientists, these plasma waves produce actual sounds you can hear. The story of how scientists found this specific hum is genuinely fascinating. For years after Voyager 1 entered interstellar space, its plasma wave system would occasionally detect bursts of plasma. Oscillation. Sharp, momentary signals triggered when shock waves from solar eruptions traveled all the way out to the heliopause and rippled through the interstellar medium. Astronomers describe these as brief, dramatic events, like hearing a clap of thunder in an otherwise quiet sky. Useful snapshots of electron density at specific moments, but rare, occurring roughly once a year at most. That left the picture of what interstellar space actually sounded like between those events frustratingly sparse. Then, in research published in May 2021 in the journal Nature Astronomy, a team led by Stella Koch-Ocker, a doctoral student in astronomy at Cornell University, working alongside Cornell professors James Cordes and Shami Chatterjee, and instrument experts Donald Gurnett and William Kurth at the University of Iowa, reported something remarkable. Going back through Voyager 1 data from 2017 onward, they'd identified a completely different kind of signal. A faint, persistent, narrowband hum that never went away. Not a momentary burst triggered by a solar shock wave, but a constant, continuous, barely detectable emission from the interstellar plasma itself, present all the time in the quiet between storms. Ocker described it as faint and monotone, sitting in a narrow frequency band, the difference between a lightning bolt and a gentle, persistent rain. Cordes compared it the same way, like hearing a lightning burst during a thunderstorm and then it's back to a gentle rain. That gentle, constant rain is what Voyager 1 has been detecting continuously ever since. This matters for reasons that go well beyond novelty. The interstellar medium, the thin gas and plasma filling the space between stars and our galaxy, isn't empty in the way most people picture emptiness. It's a complex, turbulent environment shaped by forces on enormous scales, waves generated by our galaxy's rotation, ripples spreading outward from supernova explosions billions of kilometers wide, pressure fronts and density gradients that reveal how matter is distributed across the galaxy and how stars form from it. Measuring the electron density of this plasma precisely and continuously gives scientists something they've never had before: a running, real-time map of what the space between stars actually looks and feels like, inch by inch, as Voyager 1 passes through it. And this steady measurement has already revealed something interesting. The interstellar medium isn't uniform. It has density fluctuations, patches of slightly denser or thinner plasma on scales of roughly 1 astronomical unit. Spread across the roughly 10 astronomical units of interstellar space Voyager 1 has sampled since 2017. These fluctuations are evidence of interstellar turbulence, the same kind of large-scale chaotic motion found in Earth's oceans and atmosphere, but stretched across distances that dwarf our entire solar system. Because Voyager 1 can sample these fluctuations continuously without depending on rare shockwave events, scientists now have a steady, methodical way to map the very local interstellar medium that simply wasn't possible before. It's worth understanding exactly how Voyager 1 turns plasma waves into something resembling sound. The plasma wave system doesn't detect sound waves directly. It detects oscillations in the electric fields produced by electrons vibrating in the interstellar plasma at frequencies determined by how densely packed those electrons are. Scientists take those electrical frequency measurements and shift them down into the range of human hearing, where they become audible as tones, hums, and whistles. When NASA released an audio clip of this converted signal, it produced a faint, eerie, sustained tone, a low, steady hum like something you'd hear in the quietest room imaginable. Except this sound is arriving from 25 billion kilometers away, produced by the gas of the galaxy itself. Donald Gurnett, the longtime principal investigator for the Plasma Wave Instrument at the University of Iowa, described this kind of plasma wave data as strong confirmation that Voyager 1 had genuinely left the heliosphere and entered interstellar space. The sound itself was part of the evidence. One more genuinely strange finding feeds directly into why scientists are so determined to keep the spacecraft alive. In 2020, Voyager 1's magnetometer registered a sudden jump in the intensity of the magnetic fields in the interstellar plasma it was passing through, and its plasma detector measured a corresponding rise in plasma density. Scientists had seen brief transient jumps like this before, caused by solar shock waves compressing the interstellar medium as they passed through, but those jumps had always faded back to baseline within a few months. The 2020 anomaly didn't. The elevated magnetic field and plasma density persisted, month after month, far beyond anything a solar shockwave could explain. Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center and principal investigator for Voyager 1's magnetometer, offered one striking possible explanation: that Voyager 1 may have drifted into a small, ancient cloud of interstellar plasma carrying a higher magnetic field than its surroundings, left over from a completely different star or star-forming region long ago, essentially crossing an invisible boundary between the remnants of our own sun's influence and the ancient remains of some other star's history. Scientists can't confirm this without more data, which is exactly why the 2023 communications blackout was so frustrating, and why restoring the spacecraft's ability to transmit again in 2024 felt like such a significant reprieve. Every month of data Voyager 1 can still collect might resolve this mystery, show the anomaly has finally faded, or reveal something even stranger. It's worth pausing to appreciate the engineering here, because the scale of what this spacecraft was built with and has endured is honestly difficult to absorb. Voyager 1's entire computing system has roughly 70 kilobytes of memory. A single low-resolution photo on a modern smartphone takes up more space than that. Its main transmitter generates about 22 watts of power, roughly the same as a refrigerator light bulb. By the time that 22-watt signal crosses 25 billion kilometers of space and reaches the enormous dish antennas of NASA's Deep Space Network, it has lost virtually all its strength. The received signal is billions of times weaker than it started, and NASA's antennas, some of them 70 meters wide, have to strain to detect it at all. And yet, that faint, barely there whisper, produced by a transmitter no more powerful than a refrigerator bulb, on a craft built in a decade when handheld calculators were cutting edge, carries real scientific data about the interstellar medium that no other instrument anywhere can provide. Voyager 1 launched with 10 science instruments. As decades passed and power declined, those instruments were switched off one by one, each retirement a small scientific loss traded for the survival of what remains. The imaging cameras went dark in 1990. The ultraviolet spectrometer followed. The cosmic rays subsystem was powered. Down in February 2025, the low-energy charged particles experiment, the LECP, went dark on April 17, 2026. What remains are the plasma wave system and the magnetometer, two instruments measuring the electromagnetic fabric of the space Voyager 1 is passing through, and the last two direct first-hand sensors humanity has in interstellar space. When they finally go dark, nothing will replace them. No successor interstellar mission has been approved, funded, or built. The earliest any new interstellar probe could realistically be launched and reach Voyager 1's current position would be decades from now, long after the scientific window on whatever Voyager 1 is currently measuring has permanently closed. Now, where things stand in 2026, because the story has taken several genuinely dramatic turns recently. First, the infrastructure that makes any of this possible. The Deep Space Network, a global system of enormous radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia, deliberately spaced around the world so that, as Earth rotates, at least one is always pointed the right way to talk to deep space missions. The largest antennas are 70 meters wide, roughly as tall as a 20-story building, and among the most precise radio receivers ever built. Even so, the signal arriving from Voyager 1 is so faint after crossing 25 billion kilometers that it carries only about 160 bits of data per second at most, millions of times slower than a standard home internet connection. Everything Voyager 1 has told us about interstellar space has arrived at that trickle, painstakingly accumulated over months and years of continuous listening. After years of steady scientific data, Voyager 1 hit a serious crisis in November 2023, when a corrupted chip in one of its flight data system computers turned its transmissions back to Earth into unintelligible garbage. For 6 months, one of the most scientifically productive spacecraft ever built was effectively unable to communicate. Engineers at JPL worked the problem from over 20 billion kilometers away, essentially rewriting the software controlling the spacecraft's communications remotely, with every command taking more than 22 hours to arrive, and every response another 22 hours to come back. By May 2024, they'd restored Voyager 1's ability to send back usable data, in what was widely described as one of the most remarkable remote engineering feats in the history of space exploration. But even after that recovery, Voyager 1 faces a challenge that can't be fixed away. The spacecraft runs on 3 radioisotope thermoelectric generators, converting heat from decaying plutonium-238 into electricity, generators that have been losing roughly 4 watts of power per year since 1977. By April 2026, they were producing less than half their original output. That steady decline forces NASA engineers into a delicate, ongoing balancing act. Every watt saved by turning off one system is a watt available to keep something else running. If power levels drop unexpectedly and trigger the spacecraft's automatic undervoltage fault protection, that system shuts down components on its own, and recovering from an unplanned shutdown could take weeks of careful remote work, each round of commands taking nearly 2 days to send and confirm. That's almost exactly what happened in February 2026. During a routine roll maneuver on February 27th, Voyager 1's power levels dropped unexpectedly, bringing it dangerously close to triggering that fault protection. To stay ahead of the threshold, NASA made the call to manually shut down the LECP on April 17, 2026, an instrument that had run almost continuously since 1977, measuring ions, electrons, and cosmic rays, and providing critical data on the structure and pressure of the space beyond the heliosphere. Turning it off wasn't a decision made lightly. Engineers left a tiny half-watt motor component running inside it, specifically to preserve the option of restarting it later if enough power can be freed up. Shutting down the LECP is expected to buy Voyager 1 roughly 1 additional year of operational breathing room. During that window, NASA is finalizing a high-stakes power management upgrade nicknamed the Big Bang, swapping out a group of older power-hungry components for lower-power alternatives, all in one coordinated operation. The name reflects how significant and risky the procedure is. The team plans to test it first on Voyager 2, which has slightly more power to spare and is closer to Earth, making it the safer test subject, with tests scheduled for May and June 2026. If those go well, the same upgrade will be attempted on Voyager 1 no earlier than July 2026. If the Big Bang succeeds, it could keep both Voyager spacecraft operational with at least one functioning science instrument each, well into the 2030s, and might even free up enough power to restart the LECP on Voyager 1. If it fails, the consequences could be severe and potentially irreversible. Consider what it means that NASA's mission team remains publicly committed to keeping both Voyagers going for as long as possible. These are spacecraft built in the 1970s for a mission meant to last 4 years, running on computers with a fraction of a modern smartphone's memory, powered by nuclear generators now. Approaching 50 years old, operating in an environment no instrument on Earth can simulate or test, communicating across a gap so enormous that a single command and response exchange takes 2 full days. And they are still out there, still transmitting, still collecting data nothing else in the world can replicate. The 2 science instruments still active on Voyager 1, the plasma wave system that detected the hum we started with, and the magnetometer, measuring the magnetic fields in the interstellar plasma, are quietly doing something no other human-made object has ever done, directly measuring the properties of the interstellar medium in real time, from inside it. Every piece of data Voyager 1 sends back is a first-hand measurement from a place no spacecraft has ever reached before, and there's no substitute for it anywhere, not from any telescope on Earth or in orbit. It can only come from a machine approaching its 50th year, drifting alone through interstellar space, still humming along, still listening to the sounds of the galaxy around it. That's the real story here. Not a dramatic, sudden revelation, not an alien signal, but something arguably more profound. A spacecraft humanity launched before most people watching this were born, now drifting one full light day from home, picking up the quiet, continuous hum of the interstellar gas between the stars and sending that data home across an almost incomprehensible distance, giving scientists their first continuous, real-time map of the most remote environment any human-made object has ever entered. And against every reasonable expectation, it is still doing that today, even as engineers work through a careful, high-stakes power management operation just to keep it listening a little longer. Think about the full arc of this mission. In 1977, engineers built a spacecraft with the computational power of a basic pocket calculator, loaded it with scientific instruments, pointed it at Jupiter, and launched it into the sky, hoping it would last 4 years. It has now been operating for 49 years. It has flown past Jupiter, past Saturn, past the outer solar system, through the heliopause into interstellar space, and it is still going, still transmitting, still detecting the faint electromagnetic hum of a galaxy that existed for billions of years before the first human being ever looked up at the night sky and wondered what was out there. On November 15th, 2026, it will sit exactly one full light day from the planet that built and launched it, farther from home than any human-made object has ever been, and it will still be listening. If there's one thing this whole story demonstrates, it's that the universe doesn't yield its secrets easily or quickly. The interstellar hum Voyager 1 detected wasn't a sudden, dramatic announcement. It was a faint, persistent signal scientists had to work years to identify and understand. The plasma cloud anomaly that began in 2020 still has no fully confirmed explanation. The Big Bang power upgrade that could keep these instruments alive into the 2030s hasn't yet been proven to work. Every answer Voyager 1 has given us has arrived slowly, quietly, across a gap of billions of kilometers, at a trickle of data barely faster than the earliest days of the internet, and yet every piece of it is irreplaceable. There's nowhere else in the universe humanity can currently go to get it. If you want to keep following this story as the Big Bang procedure unfolds on Voyager 2 this summer, as the same upgrade is eventually attempted on Voyager 1, as that one light day milestone arrives in November 2026, and as whatever comes next slowly makes its 23-hour journey home to Earth, hit subscribe now, because there's genuinely no other mission in the history of human spaceflight quite like this one, and no story in space science right now that's more quietly, persistently remarkable. Drop a comment and tell me what surprised you most. That this spacecraft is still working after 49 years in space, that a signal now takes more than 23 hours just to arrive from it, that the hum of interstellar space it detected is a real sound you can listen to right now, or the sheer scale of what the Big Bang upgrade is going to attempt from 25 billion kilometers away. Thanks so much for staying all the way to the end. I'll genuinely see you in the next one.